Hello dear students. So in B2A series, today we are going to start with thin lenses. So without wasting any time, let's start already. So what exactly is a thin lens? Okay, so let me first define it. Okay, uh, a lens in general is a transparent refracting medium bounded by curved surfaces. That is the definition of a lens. Let me repeat. If you want to write it down, you can go over this definition multiple times and write it in your notebook. You should do that actually. I'll repeat. A lens is a transparent refracting medium bounded by curved surfaces. What do I mean by this? Let me show you. So suppose this is a sphere and this is another sphere which may have the same radius or which may have a different radius. Now I have deliberately drawn them in a manner that there is a overlap between the two spheres, and if I choose to fill the region of overlap with a transparent medium such as glass, okay, then I'm going to call this as a lens. So I'll go over the definition of lens again. A lens is a transparent refracting medium bounded by curved surfaces. Okay, so that is what a lens is. So this is one type of lens. We can also create a lens by using, let's say, a sphere and let's say a plane. Now you may argue here that, sir, you just now said that lens is a transparent refracting medium bounded by curved surfaces. So why are you using a plane surface? Because we can view a plane surface as a sphere or a spherical surface having infinite radius. So even this qualifies to be called as a lens. Okay, in fact I'll just write their names. And a third option that we can do is that we draw one sphere like this and we draw another sphere like this. So here also you see that there are some regions. So okay, so these are the three type of lens. Now I'll write their name in a short while, but these are three lenses. And when we say thin lens, what does that mean? When we say thin lens, it basically means that this thickness would not be too great. Like the two curved surfaces, they are very close to each other. This thickness is not too large. Okay, this thickness, the maximum thickness that you see in a lens is not too large, is what we mean. What are the other options to get a lens? Okay, so the other option is to draw a sphere like this and to draw another sphere like this, where you are deliberately ensuring that they are not overlapping with each other now. And now if I fill this space, if I fill this space with a refracting medium, then it would create a particular kind of lens, the name of which I'm going to write in a short while. Similarly, on the previous slide also, I started by using two spheres. Here the spheres were intersecting with each other. Here they are not intersecting with each other. Then I went with a spherical and a planar surface. So let's do that again. A spherical and a planar surface, but they are not intersecting with each other. Okay, so this time, this would be one kind of lens. Okay, and the third kind of lens here, you probably would have guessed that here again we used two spheres and they were intersecting, but they were intersecting in a different manner as compared to this. So here again, we can go with two spheres which are non-intersecting, and we can make them non-intersecting in a slightly different kind of way, like this. Okay, so we have drawn six varieties of lenses. And here you will notice that the three varieties, they are all made up of intersecting surfaces. They are all made up of intersecting surfaces. And the next three variety, all of this, they are made up of non-intersecting surfaces. So these are all made up of non-intersecting surfaces. Okay, now all the lenses which are made up of intersecting surfaces, they are classified as convex lenses. Okay, they are all classified as convex lenses, and the ones which are made by non-intersecting surfaces, all of these are classified as the concave lenses. These all are classified as concave lenses. And within these two categories also, understand that convex lens and concave lens are two categories. Within these two categories also there are different names. For example, this one, okay, this particular one is called a biconvex lens. It is called a biconvex lens. And within this also, in case if the two radii were equal, okay, if the two radii were equal, then instead of biconvex we can use equiconvex. You know, when we use the word equiconvex, it conveys an additional information. It tells us that we are dealing with a biconvex lens. It also tells us that we are dealing with a biconvex lens such that the two radii are equal. Okay, so equiconvex. So equiconvex lens is a biconvex lens for which the radius of the two surfaces are equal. Okay, now what do we call this one? This one is called a plano-convex lens, and we call this one as concavo-convex. So you see that whichever category the lens belongs to, the name ends with that. So biconvex, the name ends with convex, plano-convex, concavo-convex, and similarly you probably you would have guessed that this one should be called as biconcave. And just as in the previous case, if the two radii are equal, then we can call them as equiconcave. So if R1 is equals to R2, then we use the word equiconcave. This one is plano-concave. Okay, this one is called plano-concave. And this one, what would it be called? Convexo-concave. Okay, this one would be called as convexo-concave. Okay, so we have looked at two categories of lenses: the convex lenses, which are made up of intersecting surfaces, and the concave lenses, which are made up of non-intersecting surfaces. Now there are some other terms. We need to familiarize ourselves with those terms. So let's see what are those terms. So when we speak about lenses, there are some terms that we use repeatedly. Let's see what are those. So the first one is you can say optical center. Okay, the first one is optical center. So you can say that this is the central point of the central point of lens. What is the speciality? Okay, it is actually a point in the lens through which a ray goes undeviated. Okay, its speciality is what? Its speciality is that a ray through optical center goes undeviated. It doesn't matter whether it's a convex lens or a concave lens. Okay, so that is the speciality of optical centers. Okay, so that is first term. The second term that we must familiarize ourselves with, okay, the second term would be the optical axis. Okay, in the case of mirror, we generally use the word principal axis. In case of lenses, we mean the same thing intuitively, but we call it as an optical axis. So what is an optical axis? It is the line joining the two centers of curvature. Okay, line joining the two centers of curvature. What do I mean by this? So think about a biconvex lens. Okay, so this has been made by two surfaces, spherical surfaces. Those spherical surfaces must be having a center of curvature. So if we join the two centers of curvature, so this line is called the optical axis. Now similarly you can draw for other category of lenses. Now if you are wondering that, sir, in case of a plano-convex and a plano-concave lens, we don't have two centers of curvature because one surface is a planar surface. Then also, if you give it a little bit of thought, you will realize that you could have answered this question yourself also. Like probably you have found the answer yourself. Let me show it to you how. So if I draw one surface like this and the other surface, and if I ask you that I'm looking for a line which passes through the centers of curvature of both the surfaces. Now we only have one center of curvature here. Okay, so if I tell you that, am I looking this as a possibility, what will you say? What will you say? Like, does it look like that this will pass through the center of curvature of a surface, the radius of which looks infinite? Like, I know that you intuitively know that this is not right. The one which is right would be perpendicular to the planar surface. Don't you think that? Because if we are considering this as a sphere of infinite radius, and we are trying to draw a line which is passing through the center of curvature of that sphere, then this line should become perpendicular to this, because a line passing through center of any sphere is perpendicular to the surface. Okay, so on that logic, so my point is that optical axis is something that can be identified intuitively also. Definition wise, it is the line joining the two centers of curvature, but it is very easy to identify the optical axis intuitively also. Okay, now we'll move to the next point. We'll move to the next term. So the next term is what we call as the first focus. Okay, unlike the case of mirror where we have only one focus, we talk about only one focus. In case of lenses, we have two focus. So what is it? So okay, an incident ray passing through F1 becomes parallel to optical axis, okay, or appears to become parallel after refraction. Okay, so basically it is a point on optical axis such that an incident ray passing through this point, that is F1, becomes parallel to the optical axis after refraction. Okay, or it appears that it has become so let me show you the ray diagram that will help you to understand. So suppose this is a biconvex lens. Now guys, there is one point I want to highlight here. Generally, when we try to draw a convex lens, you will find people. When I say people, what do I mean? I mean teachers, academicians, people who have studied this chapter, anyone who has been familiar, they generally tend to draw the biconvex lens. Okay, but it is not necessary. Like, the point is that if you're trying to depict a convex lens, you can even work with a plano convex lens, you can even work with a concavo convex lens, but this is the general habit that has developed in everyone. Teachers have been using this method, and the students have been following, and when these students become teachers, they also keep on following the same practice as I am doing. Okay, so generally if I'm trying to depict a convex lens, it is not necessary that it has to be a biconvex lens, but generally people do that. It can be any kind of convex lens. Okay, the property will remain the same. What kind of property am I talking about? So there will be a point on the principal axis such that a ray coming from it will become parallel to principal optical axis after refraction. So this point is called the F1, or the first focus. Okay, now if we are talking for a concave lens, okay, for a concave lens, F1, the ray diagram depicting F1 would look like this. The ray comes like this and then it becomes parallel. So this point is F1. Are you getting it? Okay, so this is an incident ray which is passing through F1, okay, and after refraction it becomes parallel to the principal axis. So this is what we call as the first focus. Okay, similarly there is another focus which is defined for lenses, that is called the second focus. Okay, second focus is also called the principal focus. It is also called principal focus. Okay, now what is second focus? So it is a point on optical axis such that an incident ray coming parallel to optical axis passes through this point after refraction. Again, what do we mean by this? Let me show it to you using ray diagram. So suppose this is a convex lens and we sent a ray which is parallel to the principal axis. So after refraction, wherever it cuts the optical axis, that point is called the second focus or the principal focus. In case of concave lenses, the diagram would appear somewhat like this. We'll send a ray which is parallel to optical axis, then this ray will diverge and this point will be called. Okay, so first focus, second focus. In case of first focus, the ray becomes parallel to optical axis after refraction, and wherever it was cutting the optical axis before refraction, that point is first focus. In case of second focus, the ray is initially parallel. It was coming parallel to the optical axis, and wherever it cuts the optical axis after refraction, that point is called the second focus or the principal focus. Okay, the optical center is somewhere here. Okay, the optical center is somewhere here. I don't know whether I drew it or not. So optical, okay, I did not depict optical center. So if this is a lens, optical center would be somewhat this. Okay, here also if this is lens, then optical center would be almost the middle point. Okay, now there is another term that we need to familiarize ourselves. That term is focal length. Okay, so focal length of a lens is the distance between optical center and the second focus. Okay, it is distance between, I'll simply write F2 and O. Okay, which basically means if I go to the previous diagram, okay, then this length is the focal length. Okay, and here this length is the focal length. Okay, these two lengths are the focal length. Now if we go with Cartesian sign convention, we talked about Cartesian sign convention when we discussed the mirror. Okay, so if we go by Cartesian sign convention, then you can make this rule that focal length for convex lenses is positive. Okay, and focal length for concave lenses is negative. This is when they are in air. Okay, or you can say that when lens is surrounded by rarer medium. I'll actually present this statement in a better manner. You can instead write that F for, let's make it a better statement. Okay, focal length for converging mirrors or converging lens is positive, and focal length for diverging lens is negative. Okay, now some of you may have studied this chapter somewhere, or you must some of you may be under the impression that converging lenses are convex lenses, or convex lenses are converging lenses. That means some of you may be under the impression, if you have studied this chapter elsewhere, or read some text or whatever, you may have got this impression that convex lens and converging lens, these are synonymous terms. That means some of you might be under that impression. Now if that is the case, then it is wrong, guys. It is wrong. There are situations in which a convex lens can turn into a diverging lens. Okay, and what is that situation? If you put any lens, any convex lens, let's say, in a medium which is denser as compared to the lens itself, okay, which means that if the refractive index of the medium is higher as compared to the lens, then the behavior interchanges. Okay, normally when we think about lens, we imagine the lenses to be kept in air. That means we imagine the lens to be kept in a rarer medium. And in such a situation, what kind of situation? In a situation when the lenses are kept in rarer medium, in those situations, convex lenses are converging in nature and concave lenses are diverging in nature. But if you keep the lenses in a medium which is denser than the lens, I'm not talking about the mass density, I'm talking about the refractive index. More density or a denser medium means a medium with higher value of refractive index. So if you keep a lens in a denser surrounding, then the behavior interchanges. the convex lenses turn into the diverging lenses, and the concave lenses turn into the converging lenses. So what you have to remember is that focal length for converging lenses is positive. You can also state this statement, in the otherwise also, in the other meaning also, that if the focal length of a lens is coming to be positive, according to Cartesian sign convention, then that lens is a converging lens. And if the focal length is coming out to be negative, then that lens is a diverging lens. Okay. So this is about focal length. Now, there is a formula which we call as the lens maker's formula. It helps us to calculate the focal length. Okay. There is a formula which is called lens maker's formula. Okay, it helps us to calculate focal length of any lens if the geometry of the lens is known to us and the surrounding medium is known to us. So what is the purpose of this formula? Let me write the purpose of this formula. Okay, this formula helps to calculate focal length of lens. Helps to calculate focal length of lens. Oh. If geometry and refractive indices of lens and surrounding okay, so if we know the geometry and if we know the refractive indices, then we can calculate. So what is the formula? Okay, what is the formula? So let me write the formula. The formula is 1 upon f is equals to mu lens by mu surrounding minus 1. Okay, now that's not all. Into 1 upon r1 minus 1 upon r2. So this formula is called lens maker's formula. Okay, this formula is called lens maker's formula. So if you know the geometry, by geometry I mean if you know R1 and R2, the radii of the two surfaces, and if you know the refractive index of the lens as well as the surrounding medium, then you can calculate the focal length of the lens. And there is something called as power. Okay, there is something called as power of lens. It is defined as 1 upon f. F is to be in meter, and that gives us the power in a unit called as diopter. Okay, it is indicated by capital D. Okay, for example, if focal length is plus 20 centimeter, okay, then we will write power as 5 diopters. Okay, this is the same thing that people who are wearing specs, they would be knowing that my power is minus 3.5, my power, like they would be using these statements to indicate the deficiency in their vision. For example, my power, my power is minus 5 around. So the lenses that I'm using, these lenses that I'm using, okay, these lenses have got power of around minus 5. Okay, or in other words, these lenses, their focal length is minus 20 centimeter, because a plus 20 centimeter will give me a power of plus 5 diopter. So if these lenses have power of minus 5, then the focal length of these lenses would be minus 20 centimeter. And because the focal length is negative, it also indicates that I'm using concave lenses or diverging lenses, because these lenses are being used in air that are surrounding. So in air, the concave lenses are the diverging lens. So these are diverging lens, which I know, if you can see the thickness of the lens in this video, then you know that this is concave. And in fact, if any of you guys are wearing specs, you can just remove it and you can check whether it is concave or convex. You will discover that most likely it is concave. Like that is the most common, the most common defect in our vision is addressed. It is corrected by using concave lenses. Okay, so most of us are wearing concave lens, those of you who have defects in vision. Anyways, coming back to focal length, this is the formula for focal length, and knowing the focal length also means that we can talk about the power of the lens. Okay, now let's spend some time thinking about this formula, or let's first use this formula and then we'll talk about this formula. Okay, so let me give you an example to indicate how this formula is to be used. Okay, so there are actually very important and some subtle points to understand regarding this formula. Okay, some queries to satiate, to satisfy. So let's say we have a lens such that the refractive index on one side is 60 centimeter and the refractive index on one side is 90 centimeter. Let's say not refractive index, the radius of curvature. The refractive index is 3/2 and let's say it is kept in air. Okay, so let's say it is kept in a surrounding of air, which means the refractive index of surrounding can be taken as 1. Okay, now suppose I ask you that, okay, tell me the focal length of this. Okay, now you may wonder, okay, from which direction is the ray coming? Okay, because if the ray is coming from left to right, then this surface, okay, let me get rid of this R1 also. Okay, we don't know which is to be called as R1. Okay, so or let me just write the number. Okay, indicate. So if the light is coming from this side, then R1, okay, the first surface would be this one. But if the light is coming from this side, then this will become R1, indicating that the focal length may change, at least giving a, prima facie, it looks like the focal length may be different when the light comes from the two sides. So let's check it. So suppose if we assume light to be coming from this side, and it is not necessary that the light has to be parallel beam, it can come from at an angle also, but I'm fixing the direction of propagation of light to decide that which surface I'm going to treat as 1 and which surface I'm going to treat as 2. So right now this one becomes 1 and this one becomes 2, because 1 is the surface where the light will hit the first. Okay, so now if I try to put in the formula, refractive index of lens is 3/2, surrounding is 1 minus 1, and then 1 upon, now notice that for this surface, for the surface that we are calling as 1, okay, for the surface that we are calling as 1, if you think about the sphere of which this surface can become a part, this sphere would be having a center of curvature somewhere here, that is towards the positive side of the lens. Remember, if the light is coming from this side, then this becomes the origin, and anything towards right or anything in the direction of the propagation of light will be given a positive coordinate. So center of curvature of the first surface lies on the positive side, and therefore R1 will be given a positive sign. So I will write plus 60 here. Okay, I will write plus 60 here. Now I have to think about the sign of R2. Okay, now the second surface is this, and if I extrapolate this, if I imagine this, I see that the radius of the second surface lies towards the negative side. So I should be using a minus 90 here. And now if I do the math, this will become 3/2 minus 1, that is half, and then 1 upon 60 plus 1 upon 90 it becomes. Of course you can finish the math, I'm not doing that, but the point is that we got some value of let's just finish it. Okay, so this will become 180, and then this will become 3 plus 2, so 5/36. So focal length is what? It is 72. I think I'm doing the right calculation. Okay, now this is the focal, and we are getting a plus 72. So this is the focal length when the light is coming from this side. Now notice what will happen if I assume the light to be coming from the opposite side, and whatever you assume, let's first see what happens and then we'll talk about it. So I said that this is 60 centimeter. I said that this is 90 centimeter. I also said that refractive index is 3/2, and we are using it in air. Now if we assume that the light ray is coming from this direction, then this surface becomes 1 and this surface becomes 2. And now if I'm putting values in the formula, I will write 3/2 by 1 minus 1, and then I will write 1 upon R1. Now notice that R1 is this surface. This is R1. I complete the circle. I see that the center of curvature is on the right hand side, and that is the positive side. Now this time this side is positive because the light is coming from this side. This becomes the origin. The direction of incident rays towards left, so anything towards the left of origin will have positive coordinate. So we will write plus 90. Notice that the radius of this one was 90. Okay, minus 1 upon, and then the other surface. For the other surface, the radius will lie on the negative side. So we will write, and do you notice that they eventually again get added up? Okay, so it is again half into the same thing that we got earlier, and therefore we are going to get the same focal length. So from here what you have to understand is that it doesn't matter that light is coming from which direction. If you have the same medium on both sides, it will not matter that light is actually coming from which direction. And why will it not matter is something that you have to observe from here, that ultimately if your direction changes, even R1, R2 changes, and their sign also changes, such that again we end up with the same value. And this will be true every time you try it out. Okay, this will be true every time you try it out. Okay, so if you have understood this part, well and good. Let me highlight another very important aspect of lens formula to you. Okay, I'll highlight another very important aspect. So what is that important aspect? So have a look at this. If I write the lens formula again here, it is mu L by mu S minus 1. Okay, and then it is 1 upon R1 minus 1 upon R2. So notice that this formula is product of two terms. It is product of two terms. Let's call this as A. Okay, and let's call this as B. So it is product of A and B. Now A depends on the materials of the lens and the surrounding. Okay, this A captures the dependence. It captures the dependence of focal length on refractive index of medium and lens, and B captures the role of geometry. Are you getting it or not? When you change the shape of lens or the size of lens, R1, R2 will change, sign of R1, R2 will change. For example, when you change a biconvex to, let's say, this one, you notice that R1 is negative and even R2 will be negative. Okay, so when you change the shape or the geometry, the signs change, the values change, and therefore the focal length changes. Okay, so notice that if we are keeping the lens in a rarer medium, then A will always be positive. Okay, A will always be positive. Okay, so you can try it out. You can try it as an exercise, that for convex lenses, all types of convex lens, okay, B is greater than 0. Okay, and for concave lenses, B is less than 0. Like B is decided by geometry. So if you are dealing with a convex lens, whether it is biconvex, whether it is plano-convex, whether it is concavo-convex, B will come out to be a positive number. And if you are dealing with concave lens, whether it is biconcave, whether it is plano-concave, whether it is convexo-concave, B will come out to be a negative number. Okay, so this is the situation regarding the geometry. Now, when medium is rarer, okay, if medium is rarer, for example, keeping lens in air, A becomes positive. Okay, and when medium is denser, okay, when medium is denser, A becomes negative. So you see that if you are dealing with a situation where medium is denser and the lens is convex, the product will become negative, turning the convex lens into a diverging lens. All right, so we have to understand that this formula has got two terms. One depends on the refractive indices of length and lens and surrounding. The other depends on geometry. Okay, so from here this thing becomes very, very clear that I'll give you a statement, see whether you agree with me or not. You have to remember this statement. The statement is that if the surrounding medium is rarer, then all types of convex lenses behave as converging. Okay, and all types of diverging lens, all types of concave lens behave as diverging. That is when the medium is rarer. Okay, if the medium is denser, and the lens is rarer, if the medium is denser, then all types of convex lenses behave as diverging and all types of concave lenses behave as converging. Okay, so that was about the lens makers formula. Okay, the next thing, the important thing that we have to talk about is what we call as the lens formula. Okay, so it is very similar to mirror formula. In fact, its usage is also very similar to mirror formula. For example, what does mirror formula do? It helps us to locate the image, to identify that in a given for a given object, for a given kind of mirror, where will the image be formed and what will be the other properties of the image, like is it going to be real, is it going to be inverted. So similarly, lens formula does all that for us in case of lens. And this formula is again very simple. It is 1 by V minus 1 by U. So the mirror formula was 1 upon V plus 1 upon U. It is 1 upon V minus 1 upon U. In fact, magnification, that is height of image divided by height of object, is V by U. In case of mirror, this was minus V by U, but here in case of lens, it is V by U. So suppose you have already learnt the formula for mirrors, then I'll just give you a simple trick to remember the formula for lens. In every formula for mirror, I'm talking about these two formula. In these two formula for mirror, replace U by minus U. Alright, so here it was plus 1 upon U in mirror. If you replace U by minus U, you get a minus sign here. In case of mirror, it was minus V by U, but when you replace U by minus U, this becomes positive. Okay, so this is the formula. I'll take up a question to indicate how to use this formula. Okay, so let me take up an example. Okay, so let me draw the situation. So suppose we are dealing with a convex lens, the focal length of which is, let's say, 30 centimeter. Now remember, if the question says that we have a convex lens with focal length of 30, it is up to you whether you want to draw a biconvex lens. You can also draw a plano-convex lens and declare that its focal length is 30. It is up to us what we want to represent. Okay, now there is an object here. The object height is 3 millimeter. Okay, and it is at a distance of, let's say, 40 centimeter from the lens. Okay, we need to know everything about the image. We want to know where the image will be formed. We want to know the height of the image, the orientation, okay, the nature. So we want to know everything. Okay, let me write it down. Okay, so we want to know location of the image, where will it be formed. We want to know size. Okay, we want to know nature, whether it is real or virtual, and we also want to know the orientation. So these are all the things that we want to know. Let's see how we are going to do it. Okay, so let me do it here. Okay, so my intention is to start using the lens formula. Focal length I will write with a plus sign. Okay, the question will just give you the numerical value. You have to decide whether you have to use it with a plus sign or a minus sign. Okay, so focal length is plus 30. Okay, the object location, see, object is located towards the left side. See, if this is the object, it basically means that rays from this will travel. Okay, rays from this will travel. Okay, and and hit the lens, so the rays are traveling towards right. Okay, so anything to the right of the lens will be positive and anything to the left of the lens will be negative. So U will be written as minus 40 centimeter. U will be written as minus 40 centimeter. Okay, and that's it. V can be calculated using the lens formula. We can rearrange this formula to write UF upon U plus F. Okay, so I will directly put the value here, U, okay, into F into divided by U plus F. So this becomes plus 120. You can check the calculation. Okay, so indicating that these rays, okay, these rays will converge. These rays will converge to a point which is 120 centimeter away, like this. Okay, and now we can see that this is the real object. The rules of calling the object real or virtual. Okay, so this is the real object. We discussed that rule earlier in one of the previous sessions. So this is a real object creating a real image, and whenever the object and the image nature are same, we get an inverted image, inverted with respect to the object. So here, because the object is upright, we will get an image which would look like this. We will get, oh, let me use another color. Incidentally, this. Okay. Now, what is the height? And the same thing can be concluded by writing height of image. Height of image would be V, that is 120, by U. U is, let me change the color, it may not be visible to the students, into height of object. So it turns out to be how much? It turns out to be minus 9. So minus indicates that we have to draw an arrow, the orientation of which should be opposite to that. So remember guys, I'm not saying that minus indicates that we have to draw a downward arrow. What I'm saying is that minus indicates that we have to draw an arrow opposite to that was given here. Now here we were given upright, therefore we are drawing a downward pointing arrow. The size would be 9 millimeter. So location is 120 centimeter towards the right of the lens. Size is 9 mm. Nature is real. Orientation is inverted. Okay, so like this, by using lens formula, we can figure out everything that we need to know for the image, of course. And we can use various kind of lens. The formula is applicable for all kind of lens, whether it is convex, whether it is concave, all kind of lens, the formula is applicable. And you need to practice this formula to become good at this chapter. All right. Dear students, there is an important announcement that I want to make. I'm pretty sure you must have come across Nidhi ma'am's video also on this channel announcing the same. Let me do it again, just in case you missed that video. So we are starting NSEJS revision camp, and this camp is going to be absolutely free for all of you. So it is a camp that you can join at 0 rupees. Here we are going to revise the NSEJS syllabus for you guys, and we are going to have a lot of tests also in this batch. So it's a batch which you can join at 0 rupees, mind you. All right, so therefore you must listen to it, because apart from your commitment towards your result, there's nothing else that we are asking from you guys. Okay, so this batch is starting from 3rd October. Okay, it is 100% free, no hidden charges, nothing, nothing guys. Okay, what are the details? What are the other details of this batch? In this batch, weekly we are going to have 2 classes. Okay, 2 classes per subject, that is physics 2 classes, chemistry 2 classes, biology 2 classes. So a total of 6 classes per week is going to be scheduled. We are going to have full syllabus test as part of this batch. Okay, we will train you on MCQ. Again, this is the pain point for many of the students. So we'll try to improve you upon your MCQ attempt. Okay, we will be giving you assignments for things that we are revising in the sessions. Okay, and of course you are going to get mentorship and guidance from us. Nidhi ma'am is going to help you to ace this exam. Okay, and we'll do some performance analysis with you. What will be the timing of the session? So guys, the general timing would be like, the sessions would be scheduled in window of 5 to 7:30. So I'm not saying that every day you will be engaged for 2.5 hours. No. Okay, generally the duration of the session would be 1 hour per session. Okay, but that 1 hour could be 5 to 6, or it may be 6:30 to 7:30. Okay, that is what we are saying here. So understand that this is the window in which the classes will be happening. Remember, there will be 6 sessions per week. Okay, assignments will be given. All right, and it includes the test series also, guys. All right, so the test series is also part of this batch. So do join the batch. And how will you do that? So guys, in the description of this session, there would be a link to a Google form. You have to fill the Google form. You have to provide your details there. We want to see that whether you have registered for NSEJS or not. And if you have registered, you share your details. So we want the genuine students to be part of this batch. Of course, it is a free batch. Anyone can join. And therefore, it becomes imperative for us to ensure that only the serious candidates or the real NSEJS candidates are part of this batch, so that they do not spoil the decorum of the batch. So fill the Google form, guys. Once you fill the Google form, our team will verify your details, and then we will enroll you into the batch. So welcome to the batch, everyone, and I'll see you in the batch. We'll see that how we can improve upon your NSEJS exam and how we can get you selected in the NSEJS exam. Take care, students. Bye-bye.